Learn like a pro.
Have you ever wondered how chemists can create those perfect, pure crystals, seemingly out of thin air? Well, it's not magic, it's chemistry. And today, we're opening up the chemist recipe book to show you exactly how it's done.
So really, how do they do it? How do you go from, say, a simple liquid and a basic solid to these beautiful, perfectly formed crystals? That's the big question we're answering today. And trust me, there's a surprisingly logical blueprint for getting it right, every single time. So here's our game plan. Everything starts with one really important question. After that, we'll dive into the three main techniques: the super precise titration method, the more hands-on excess method, and the visually awesome precipitation method. Then we'll cover how to get your final product sparkling clean. Let's get started.
All right, first things first. Before you even think about touching a beaker or a test tube, there is one question you have to answer. It determines the entire path you're going to take.
And this is it. It's that simple. Is the salt you're trying to make soluble, meaning does it dissolve in water, or is it insoluble? Your answer to this is the critical fork in the road. It literally tells you which of the three recipes from our chemistry cookbook you need to follow.
So how are you supposed to know? You don't have to guess. You just consult a table like this one. Think of it as your cheat sheet. For example, if you look at nitrates, see that? All of them are soluble. No exceptions. Easy. But then you look at sulfates and chlorides. Most are soluble, but there are those few tricky exceptions, like lead sulfate or silver chloride. Knowing these little details is the key to picking the right method from the get-go.
Okay, so let's go down the soluble path first. Let's say your salt does dissolve in water, and you're starting with two liquids, like an acid and an alkali. Well, for that, you're going to use the most elegant and precise method we have: titration.
So, to be clear, titration is your go-to method only under these conditions. You're making a soluble salt, both of your starting materials are already dissolved in water, and usually you're working with salts from group 1 metals. Think sodium or ammonium ions.
The procedure itself is a thing of beauty. First, you measure an exact amount of acid into a flask. Then, you add a couple of drops of an indicator. That's what's going to give us our signal. Next, you slowly, drop by drop, add the alkali until the indicator suddenly changes color. That's the sweet spot. You write down exactly how much alkali you used, and then, and this is super important, you do the whole thing again, but this time without the indicator, to get a perfectly pure salt solution.
Now, here's a classic mistake I see all the time. Students ask, why do we have to use that specific indicator, phenolphthalein? Why can't we just use a universal indicator? Well, the answer comes down to one word: precision.
And here's exactly why that choice is so critical. Universal indicator gives you this mushy gradient of colors. Is it green? Is it yellow-green? It's really hard to tell the exact moment you're done. But phenolphthalein, it's like a light switch. It goes from perfectly clear to a sharp, bright pink. Bam! There's no guesswork. You know you've hit the exact endpoint.
So, the bottom line is this. The indicator is just a tool to help you figure out the exact recipe, the perfect amounts of acid and alkali. But you don't want the indicator ending up in your final product. So you repeat the experiment with those exact same amounts, but you leave the indicator out. That way you know your final salt crystals are 100% pure.
Okay, cool. But what if you're still trying to make a soluble salt, but one of your ingredients is a solid that won't dissolve, like a piece of metal or a metal oxide? For that situation, we need a totally different technique: the excess method.
So this is your method when your target salt is soluble, but one of your reactants is a solid. The classic example is reacting solid copper oxide, which is a black powder, with sulfuric acid to make that beautiful blue copper sulfate solution.
The process here is much more direct. You just take your acid and you keep adding the solid, stirring and warming it up until the solid just stops reacting. At that point, you know all the acid is gone. Then comes the most important part. You filter the whole mixture. The leftover solid gets trapped in the filter paper, and what comes through is your pure salt solution, all ready to be turned into crystals.
You might be wondering, why add so much extra solid? Isn't that wasteful? Actually, it's really clever. By adding more of the solid than you need, you make absolutely certain that every last bit of the acid gets used up. That way, you don't have any leftover acid in your final product, and getting rid of the extra solid is easy. You just filter it off.
Okay, time to go back to that first big question. What if the salt you want to make is insoluble? What if it doesn't dissolve in water? For this, we use a method that is incredibly cool to watch. It's called precipitation.
This is where the real fun is. You start with two solutions that are both completely clear. They look just like water. You pour one into the other, and bam! Instantly, a solid appears out of nowhere, turning the whole thing cloudy. That solid that just formed, that's your salt. It's an incredible thing to see.
And the procedure could not be simpler. You mix the two solutions, give it a quick stir, and then you filter it. But this time, unlike the excess method, the solid you collect on the filter paper isn't waste, it's your actual product. All you have to do then is give it a little rinse with some pure, distilled water, and you're good to go.
So you've made the salt. Great. But the job's not quite done. Any good chemist will tell you that the final steps, recovering and purifying your product, are what really separate a good experiment from a great one.
So let's just recap those final steps. For your soluble salts, the ones from titration or the excess method, you get them back by turning them into crystals. For the insoluble salts from precipitation, you just filter them out. But notice the one thing they all have in common? Every salt, no matter how you make it, has to be washed with a little distilled water to get rid of any last impurities. Purity is the name of the game.
All right, our lab session is just about done. Let's head back to the desk and write up our final lab report, a summary of everything we've learned.
This table right here, this is the ultimate cheat sheet. It puts everything side by side. See how it breaks it down? You've got two methods for soluble salts, one for insoluble. You can see how titration requires two liquids, while the excess method needs a solid and a liquid. And that last column highlights the key difference in what you're actually doing. Precise measuring versus adding extra versus just mixing and collecting.
And that's really the big takeaway from all this. It all boils down to 3 methods for 2 different kinds of salts, all driven by one single ultimate goal: getting a perfectly pure product.
So there you have it. The chemist's recipe book is officially open. You've learned the logic, you've seen the techniques. So my final question to you is, if you could walk into a lab right now, what's the first thing you would want to create? Thanks for joining me for this one.